Let's explore finding the moment of inertia, and we're going to do this by finding the moment of inertia of a rod, a long thin rod about its end. And so what that's going to look like, I'm going to start by drawing my axis of rotation. So this is my axis here, and let me draw a long thin rod. So this is my long thin rod, and the only information really know about this is that it has some length L, and that is from both ends, and it has some mass M. So these are our constants in this problem, and our moment of inertia equation reads I, which is our moment of inertia, is equal to the integral of r squared dm. So how do we use this equation? Well, first, let's sort of define the variables. So I said that I is our moment of inertia. So m of I is what I'm going to abbreviate this as. R is going to be our variable of integration. And finally, dm is, it's sort of like the small piece of mass, like the infinitesimally small piece of mass that we're going to use to integrate. Remember, when we integrate, we're adding up lots of little bits, and in this case, we're going to be adding up lots of little bits of mass. Now, in this problem, we don't actually have an r or a dm, but we can sort of add these to our picture as we go along. Now, when I want to take an integral, I normally take an integral of x with respect to x, but here I have r with respect to m. I don't know if I can just do that. So what I need to do is get either r or dm in terms of, well, one of them in terms of the other. And so in this case, I'm going to get dm in terms of r and our constants. Now, the way I'm going to do that, first I have to define what these letters mean. So r means the distance from our axis to what we're integrating. So this I'm going to label r, and this is our axis, and we go out to this point here. It doesn't really matter where it is, and this is a tiny piece of the rod which has a length of dr and a tiny mass of dm. So we're finally seeing our r and our dm appear. So this tiny piece of the rod, dr, which has a length of dr, is a distance of r from our axis, and it has a mass of dm, a tiny, tiny mass of dm. Now, the way that we sort of relate all of these so we can solve our problem is using the idea of linear density. So linear density, it's sort of like the idea of volume density, which we're more familiar with. Volume density is mass per unit volume. Here, linear density, and the symbol I use is lambda, is equal to the mass divided by the length. So in the case of a long thin rod, we just divide the mass by the length, and that gives us the linear density. So if this is true for the whole rod, it's actually going to be true for the tiny piece we have here. So I can also say that lambda is equal to, in this case, my mass is dm, and my length is dr. So lambda is equal to dm over dr, in addition to being equal to mass over length. And so what I'm going to do, because these are both equal to lambda, I can set them equal to each other. So I'm going to say mass over length is equal to dm over dr. And this is just a proportion that we solve. In this case, we're going to solve it for dm because we want to get our integral in terms of dr, r, and constants. In order to do that, I'm going to multiply both sides by dr, and on the right side of the equation, this actually cancels out. So I end up with dm equals m over L times dr. And so now I'm ready to substitute this in to our moment of inertia equation here. And what I'm going to do with that is I'm going to say the moment of inertia, I, is equal to the integral of r squared, and instead of writing dm, I'm going to substitute in this equivalent expression that I found. So instead of writing dm, I'm going to write m over L times dr. So now I have one integral that is in terms of one variable, r and dr here, and then some constants, m over L. Now, when I take an integral, it's kind of nice to actually pull out any constants from my integral, so we just have less stuff going on inside of it. So I'm going to write my m over L on the outside of my integral. So I have m over L times the integral of r squared dr. Now, right now, this looks like an indefinite integral, which is an integral that you're just extending from infinity to negative infinity. But this is not an infinite length. This is a finite length. We have a rod. We can measure how long it is. And so we actually have to add bounds to it so it becomes a definite integral. So if we think about r starts here, and the distance here is 0. So we're going to start at 0, and that's our lower bound. We go from 0 all the way out to L. So L is going to be our upper bound of integration. And now we are ready to actually take the integral. So when we take an integral, we leave the constants the same. So m over L stays the same. And the integral of a simple polynomial like this, we just raise the power by 1, so it becomes r cubed, and then we divide by that power. So we have r cubed over 3, and our bounds of integration are from 0 to L. I'm going to simplify this a little bit by just combining these two fractions. They're connected by multiplication. So I'm going to say m r cubed over 3L from 0 to L. And when I evaluate this, what I do is I just plug in my upper bound first. So m times L cubed divided by 3L minus m times 0 cubed divided by 3L. Now here, over here, we have 0 to a power, which is just 0. 0 times anything is just 0. So this actually all cancels out, which makes our lives even simpler. And so when we reduce this, because I have L to the third divided by L, I'm dividing one variable by another. I subtract the exponent, so I end up with ml squared divided by 3, or just 1/3 ml squared. And that is our moment of inertia of a long, thin rod about its axis.